Hello, multivariable calculus students. This is Mr. Johnson, and this is a continuation of section 9.3. We're going to talk about the dot product formula now in component form, and you can just cross those little bit off there. That's a typo, I apologize. The formula is here, and you have seen it in the video from the Better Explained website. It is a very simple formula, one that you'll be happy that you have because it does save you a huge amount of time. And when we do the cross product formula in section 9.4, you will appreciate the dot product even more because the cross product is much longer to calculate than the dot product. And, and so I think you'll be thankful to have this. It is also easier than the formula that you used in the first couple examples where there was the cosine of theta involved. This formula is simply just multiplication of the similar components. And in the video that you watched from the Better Explained website, he talked about how the dot product is really the interaction of vectors in a directional sense. So it's like direct multiplication. And we're really just concerned about how similar components interact. That's why you see in the dot product formula that we're multiplying similar components and we're not starting to cross over. And again, that's what we're doing in section 9.4 with the cross product. Okay. Remember the outcome of the dot product is a scalar. It's a number, not a vector. It's a number. Okay. I'm going to show you just a couple of these really quick. So in example 5, we're simply just going to multiply the first component by the first component in the second vector, and then we're going to add the second component in the first vector multiplied by the second component in the second vector, and we get 6 minus 4, and our result is 2. It's as simple as that. Here are two vectors, with 3 components. So we have -1 times 6, -6, plus 7 times 2, so 14, plus 4 times -0.5, so -2, and we get -8 plus 14, so we get 6. Okay, here's an example with the vectors I, j, and k. One of the big things here is just notice that the second vector does not have an I written. That means that that component is 0. I do this all the time. I'll look at it and I'll completely skip the fact that the I is gone, and I'll end up taking the component here with the component there, and then the component here with the one there, and then I'll just tack on the other one. I'm rushing or something, I'm not really sure. So just be aware that you have to multiply these similar components. So the component in front of I is 1, however, it's multiplied by 0. And then we have 2 for j multiplied by 2 for j in the other one. And then we have -3 in the first multiplied by -1 in the second. And so we get 4 plus 3 and get 7. So there you go. That's the dot product in component form. It's pretty straightforward. Okay, let's talk about the perpendicular test. And remember, the perpendicular test says that if A dot B is equal to 0, then A and B are perpendicular. Okay, so that was that little if and only if statement that we had in the last video. So what we'll do is simply just take A dot B, and if it's 0, they're perpendicular, and if it's not 0, then they're not. It's pretty simple. So we have 2 times 5, so 10, and 2 times -4, so -8, and -1 times 2, so -2, and sure enough, it is 0, and so we could say that therefore A and B are perpendicular. Okay, we're going to move on now to the next page. Okay, in example 9, we have a question that asks for the angle between vectors A and B. Now, before doing the component form, and when we were looking just at the angle formula, we couldn't do this yet. So let me write it out really quickly. We have A dot B equal to the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between them. So in the first portion of this section, when I had the first video, we could do the second portion of this formula. We could do the calculation if we were able to calculate the magnitude of A and the magnitude of B, and if we had the angle between them, we could find the dot product. It's not real common to have the angle between the vectors, and so therefore it's more common to just have the vector components and be able to simply multiply the components together. Now, occasionally you don't have those vector components. That's why the angle formula does exist. That's, excuse me, one of the reasons it exists. In this case, we're asked to actually find the angle between these vectors. And the way we're going to do this is we're going to perform the dot product using component form. So we have, let's see, 2 times 5, so 10, plus 2 times negative 3, so minus 6, and negative 1 times 2, so minus 2. And so what we get here is 2 for the dot product of A and B using component form. We also can calculate the magnitude of A, which is the square root of 2 squared plus 2 squared plus 1 squared, negative 1 squared, which is square root of 9, which is 3. Then we have the magnitude of B, which is the square root of 25 and 9 and 2. Nope, that's not 2. Let's change that. That's going to be 4. And that's going to give us then the square root of 38. Okay, so let's put all of this in, or back into that blue equation we have. So what we have is 2 equal to 3 times square root 38 times cosine of the angle. So what we can do here is we can simply just solve for the angle, which gives us the inverse cosine of 2 divided by 3 times root 38. And if you type that into your calculator, you end up getting 83.791. So if you want, if it's helpful, you can add this formula. The angle theta is equal to the inverse cosine, or excuse me, inverse cosine of A dot B divided by the magnitude of A times the magnitude of B. It really, I mean, all it is taking this original equation and solving for the angle. That's all that is, but it's important to know that that's one of the reasons that we may want to utilize both elements of the dot product formula. Okay, let's do example 10, and then we'll kind of be at the midpoint of section 9.3. So it says that a force is given by F, moves a particle from P to Q, find the work done. So remember, the work done is the force vector dotted with the displacement vector. And what we had in the original portion of section 9.3 is this formula utilizing cosine of the angle. The problem is that we don't really know what the angle is between them. Therefore, it doesn't really make a whole lot of sense to use that side of the equation. Let's use just the component forms. But what we need is the displacement vector. And remember, the displacement vector is from P to Q. And if you think back to the first section of this chapter, all we're doing is we're subtracting, we're starting with the initial point, going to the terminal point. So from the terminal point, we have 4, and we're going to subtract 2 from the initial point to get our first component. So our vector will be 2. Then the next component will be this middle value 6 minus 1, so we get 5. And then our last one will be 2, and we subtract 0. All right, so what we have then for our work is the force vector, which is given to us as 3, 4, 5, and we're going to dot it with the displacement vector, which is 2, 5, 2. And we're going to use our simple little formula. 3 times 2 is 6, 4 times 5 is 20, and 5 times 2 is 10, and we get 36. No need to figure out some angle. No need to find the magnitudes of f or d. All we need to use is the two vectors that we have and the component form for our definition. All right, at the bottom of this page, there are some properties of the dot product. These are obviously good to know. I have talked about some of them. I will talk about more of them as we continue and as we do some different proofs and things like that. That is the stopping point of this video. What we're going to do in the remaining videos for section 9.3 is do a proof of the dot product as well as analyze some kind of neat stuff which are called projections utilizing a bunch of these formulas. Thank you.